In this video, we're going to talk about Taylor and Maclaurin series. So let's suppose that we start off with a function that has a power series representation. It's centered at A and has some non-zero radius of convergence. From the previous section, we know that that means the power series itself is differentiable and so is f. So we can start doing some equating of things. So first, if we substitute x equal to A, well, certainly every term except for the c sub 0 is going to cancel out on the right-hand side. There will all be zeros in all those terms. So our f of A has to be c sub 0. Like I mentioned before, we know that f is differentiable, so we can take the derivative of both sides. The derivative of the right-hand side, of course, we're just using power rule here. The c naught will go away. We'll just get a c1. Plus 2c2x minus a, plus 3c3x minus a squared, so on up the line. Plugging in a again into the derivative, well, the derivative will just be f prime of a, of course. But on the right-hand side, all of these things are going to cancel out again. The only thing we're left with is c sub 1. So c1 has to be equal to the derivative of the function at a. Second derivative, when we take a second derivative, notice here the 1 would come down. You get a 2 times 1 times c1. I guess I should do it here. 2 times 1 times c1, 3 times 2 c3 x minus a to the first, 4 times 3 c4 x minus a to the second, and so on. So if we solve for c2, we get f double prime of a over 2. For the third derivative, same idea. This one would have a power of 1 on it, so you get 3 times 2 times 1, c3. Here we get a 4 times 3 times 2, c4, x minus a, and so on up the line. Again, plugging in a for x and solving for c3, we get the c3 is the third derivative at a over 3 factorial. If you go through the next step, you'll get that the c4 has to be the fourth derivative evaluated at a divided by 4 factorial. And we start to see a pattern. The coefficients, the c sub n's, have to be, this is a typo, have to be, the coefficients have to be the nth derivative. This should say nth derivative right here, not a 0. That should be an n. My apologies. This should be the nth derivative evaluated at a over n factorial x minus a raised to the nth power. This expression is referred to as the Taylor series of f at a. It pops up often enough that we have thing centered at 0. We've talked about that before. So if a is equal to 0, this again should be the nth derivative, not the 0th derivative, which is just the function. It should be the nth derivative of 0 over n factorial x to the n. This is referred to as the Maclaurin series of f. So let's see if we can find a Maclaurin series for f of x equals natural log of 1 plus x. And we're asked to find the radius and interval of convergence. So the first thing we need to do is find a general formula for the nth derivative at 0. And that's just going to involve taking some derivatives. All right, we plug in 0 to the original function, we get 0. First derivative is 1 over 1 plus x. Evaluated at 0 is 1. Second derivative is negative 1 over 1 plus x squared. Put in 0, we get negative 1. Third derivative is 2 over 1 plus x cubed. Evaluated at 0, we get 2. Fourth derivative is negative 6 times 1 plus x to the fourth. Fourth derivative evaluated at 0 is negative 6. Fifth derivative, well, we're going to get a positive 24 times 1 plus x raised to the fifth. Plug in 0, we get 24. Notice where these are coming from, right? Because I'm just thinking of this as 1 plus x to the negative 1. That's why the signs are alternating, right? Bring the negative 1 down in front, make it a negative 2. Bring the negative 2 down in front, make it a negative 3. Bring the negative 3 down in front, make it a negative 4, and so on. All right, so what's happening here? Well, when I put in, well, certainly the signs are alternating. Positive, negative, positive, negative, positive. What's going on with the numbers? Well, I recognize these as 1, 1, 2, 6, 24. They're factorials. This is 0 factorial, 1 factorial, 2, 3, and 4. Well, notice that this is 0 factorial for first derivative, 1 factorial for second derivative, 2 factorial for third derivative, and so on. So it's n minus 1 factorial here. All right, so the formula says do the nth derivative evaluated at 0, so that was the formula we just found, over n factorial times x to the n. Our constant term was 0, so we're starting this series at 1. This simplifies a little bit, right? This just simplifies as 1 over n. So we get negative 1 to the n plus 1 over n times x to the n. And this matches the power series representation we had for natural log of 1 plus x in the previous section. Here's what it looks like if we expand it out. Just for mixing things up a little bit, let's find the radius of convergence by using the root test. So raise everything to the 1 over n power and take an absolute value. Take a limit. Absolute value makes the negative 1 go away. The n and the 1 over n will cancel. We just left with the absolute value of x. And then n to the 1 over n here. This is a limit that we should recognize. If not, you can go through and do some L'Hopital's rule after doing a log of it. But in particular, that limit's going to be 1. And we just get absolute value of x. So we need x to be less than 1 for the series to converge. So our radius of convergence here is 1. Which is not a huge surprise because, like I said, this is agreeing with what we did in the last section, finding a power series for natural log of 1 plus x using the geometric series, what we did in that previous section. We can check the endpoint convergence. If we put a negative 1, we'll get something that diverges because we get the negative harmonic. If we put in positive 1, we get the alternating harmonic, and we get it converges. So the interval of convergence will be negative 1 to 1. Let's do another example by finding one of these through by definition, but let's do a Taylor series, so this will be centered somewhere else. Let's do this Taylor series for e to the x centered at natural log of 2. Well, this is a very, very easy thing to differentiate because no matter how many times we differentiate e to the x, we get e to the x. So the nth derivative evaluated at log of 2 will be 2, no matter what. So our Taylor series for e to the x here will be the sum from n equals 0 to infinity of 2 over n factorial times x minus log 2 to the n. Defining its interval of convergence, radius of convergence, and interval of convergence, let's do the ratio test. Again, ratio test here would be the appropriate one to use because of that n factorial in the denominator. Limit of the absolute value of the ratio of consecutive terms. We get 2 over n plus 1 factorial times x minus log 2 to the n plus 1 over 2n over n factorial times x minus log 2 to the n. The absolute values don't do anything to the n factorial, the n plus 1 factorial. The 2's will cancel each other out. When we simplify the x powers, we'll just get absolute value of x minus log 2. And that'll be over n plus 1. X here is fixed. So no matter what value we plug in for x, as long as it's fixed, when we do the limit, well, n's getting bigger and bigger and the top stays the same, so this is going to go to 0. So no matter what we plug in for x, we always get a limit that's less than 1. So the radius of convergence is infinity, and the interval is minus infinity to infinity. All right, we've mentioned several times before that one of the primary reasons for studying power series is to do approximations. Well, if we're doing approximations, we would like to know how good our approximations are, and so that's what we need to worry about doing remainders. So to that end, let's talk about what we mean by a Taylor polynomial. If we have a Taylor series representation for f of x, the nth degree Taylor polynomial just says take that power series and write a polynomial, stopping it somewhere, in particular at n. Okay? So the remainder associated with this Taylor polynomial will just be the difference between the function and whatever the Taylor polynomial is. So, one of the things that we would like to know, of course, is whether or not the function is actually equal to the sum of its Taylor series. What that means is that, is there a non-trivial interval, something other than just x equal to a, that the function is actually equal to the Taylor series? Because certainly we can make a function and have a Taylor series for it, but maybe it only converges at the center, and that's not very useful. So, we want to make sure that we have a useful Taylor series, something that actually has some interval of convergence that will give us values that are close to the function value if we're using Taylor polynomials to approximate it. So the way that we can get this is to show that the remainder goes to 0, and if the remainder goes to 0 for all x that is in that interval for x minus a is less than r, then the function will be actually equal to the sum of its Taylor series. Typically, the way we show that the limit goes to 0 is to show that the remainder is bounded by some values. Okay. So if the nth first derivative is bounded for all x minus a within a certain region, then the remainder is going to be less than the capital M over n plus 1 factorial times x minus a to the n plus 1 for all x in there. So anyway, what this says is if our first derivative is bounded for all x minus a in some interval, then our remainder is less than or equal to this value. Well, m will be fixed because we have the bound here on this. So m's not changing, right? This is the bound for the n plus first derivative. And we're looking for fixed values for x in this interval, right? We'll pick a value for x in this interval and plug it in. Well, this is a constant. And we want to know that this, what happens with this limit as n gets very, very large. That's what we're doing. All right, so let's go back to the previous example to see what's going on. Okay, there's a lot of symbols and words and so on, but let's see what's going on. Our function here is strictly increasing, and the derivative is e to the x for all n. That tells us that our n plus first derivative is e to the x. For any d that we have that's bigger than 0, we know that e to the x will be less than or equal to the e to the 2 plus d, because 2 plus d, again, this is increasing function, right? So if I plug in something in here, well, the endpoint for this interval is 2 plus d. So any x that I plug in, where x minus 2 is less than or equal to d, has to be less than e to the 2 plus d. All right, so for Taylor's theorem, we have that the remainder is less than or equal to e to the 2 plus d over the n plus 1 factorial times x minus 2 to the n plus 1. All right, so n's going, this is a constant, so that's not going to affect our limit very much here. But what happens here? For a fixed x, this is a number raised to the nth power, and this is a factorial. Well, factorials get bigger faster than a single number, a fixed number going off to infinity. Okay? So this will get smaller and smaller and smaller, so this limit really does turn out to be 0. The absolute value of the remainder has to be less than this value, so the remainder is going to 0, which means that e to the x is the sum of its Taylor series. All right. So some often used Maclaurin series that we have are these. If you go through the definition for Maclaurin series, we didn't go through all of them. We didn't go through any of them, but these all pop up quite often. Here's e to the x, here's sine of x, cosine of x, log of 1 plus x, and inverse tangent of x. So you can go through the definition and see that these really are the Maclaurin series for these. What we'll want is a base of functions, power series representations for functions that we can use to find new power series representations. Let's do an example. Let's say we want the Maclaurin series for the integral of f of x dx, where f of x is this piecewise defined function, sine x over x if x is not equal to 0, and 1 if x equals 0. This function is nice because it really is continuous and differentiable everywhere, even though we have a piecewise defined function. Let's see how we get a Maclaurin series representation for this. Start with our Maclaurin series representation for sine and divide it by x. We divide it by x. It's just going to take this power from 2n plus 1 down to 2n. So we get negative 1 to the n, x to the 2n, over 2n plus 1 factorial. We can check that this actually does match that f of 0 is 1. If we put n equals 0 here, we get x to the 0, that's 1. Remember, x to the 0 is 1 for our purposes in these power series. Negative 1 to the 0 will be 1, and 1 factorial is 1. So we really do get 1 out of this power series when we plug in 0 for n. Or 0, I should say 0 for x, but the first term is 0 as 1. I'm sorry, the constant term is 1. All right, so now to find a Maclaurin series for the antiderivative, we'll integrate term by term, add 1 to the exponent, divide by the new exponent. So there's our Maclaurin series for the indefinite integral, and of course we have, since it's an indefinite integral, we have the plus c sitting there. Another thing that we can use these Maclaurin series for is to find some limits. So say we want to use Maclaurin series to evaluate this limit as x goes to 0 from the right of 1 minus cosine root x over inverse tangent of x. All right, so here's the Maclaurin series for cosine with root x plugged in for x. Here's the Maclaurin series for tangent. Let's just write it out longhand. For this one, notice the 2 will take care of the square root, so we just get x to the n here. So your first term will be 1, the next term will be a minus x over 2 factorial, the next one will be a plus x squared over 4 factorial, x cubed over 6 factorial, and so on down the line. For inverse tangent of x, you put in 0, you get x, you put in 1, you get x cubed over 3, put in 2, you get x to the 5th over 5, and so on, and they're both alternating. Notice the 1's cancel on top, and then we can flip, when we take this negative sign and distribute it through, it flips all the signs on the other ones. On top and bottom, we can factor an x out of every single term and cancel them. So now, notice that we can plug 0 into the denominator. We have no issues now, just like what we did before with limits back in Calc 1. So now if I plug in 0 into the bottom, I get 1. Plug in 0 into the top, I get a half, so the limit turns out to be a half.